in the Dash meeting, we wanted to cover possibly a 10-minute Q&A from Prince regarding the presentation last week he had provided on the Sonic HLD. And we also wanted to allot a nice chunk of time for Chris to go over the test automation pipeline. So if we could get started, Prince, or did anyone have comments or questions for Prince ready to go based on the HLD from last time? Okay, if we don't have anything, we maybe could move that to the end or put it in the chat window and let Chris go ahead.
Okay, I'll get started.
Let's do that.
Let me start by sharing my screen. Good morning, everybody. Good evening, wherever you reside. So I wanted to go over the latest pull request, which is 127. I just issued it last night, and something we've been working on for a few weeks. The primary goal is to automate the Sirius pipeline build and put in a first traffic test using the XCC traffic generator to plant the seeds to start building more and more test cases against the data plane. And Marian created this Sirius pipeline directory with all the build artifacts and make files, etc., and Docker files quite a while ago. And so we just built upon his work, which was already pretty thorough and ready to go. So what we did was we added automation in the Git pipeline. We added spinning up traffic generators, tried to add a lot of documentation, and made a few structural changes and make file improvements, tried to make it a little more usable because we've added quite a bit of complexity for all the automation and testing. So that's the overview. And what I want to do is walk through the README file. And I'm also going to try to do a couple of demos. So the first thing I want to do is show you this menu item here, which people may or may not be familiar with, but this is the entryway to your CI or continuous integration automation features of GitHub. And GitLabs has an equivalent. Let's see, no, that's the wrong repo. Let's go to the correct repo. No, that's where I want to be. I want to go to where this pull request is. It is sitting on a fork that Deanna, my colleague, created. And that's where the development branch is right now. So the pull request, you can see it in the Azure. You can see it in the Azure repo. It'll show all the changes. But the actual fully running version of it is right now in this dev branch, which is the typical GitHub workflow. And so if you want to play with this, what you want to do is go to the source, which is this repo, and clone it or do a pull request. Do a clone and then run all the instructions. So first thing I want to do is show you this menu here on actions. This will be new to some people. This shows all these workflows that have run in the past in this repo. And what these are is these are the results of all the last commits and pushes that have been done to this. So here's one where I deliberately created a P4 code error on purpose to demonstrate that it shows a failed build. And then here's where I fixed it. And I'm going to go through some of this. So that's one thing, is that there's this actions history. You can go through and you can drill down. So I'm going to drill down into this particular run. And what you get is this big log of everything that happened. And I'll actually demonstrate this by doing a commit. So you can see this line of code here, import do.p4. It's a little joke. It's a deliberate error. And the build failed because there's no such file. In fact, there's not even an import statement in P4. So it's two mistakes. There's missing file and there's this import, which doesn't even make sense in P4, the Python keyword. So that's a failed build. And here's a good build.
Cool.
So see, it just goes through, everything's done. And you can go through and look at all the steps. You can drill down and, here's the same P4 switch being built. And, no errors, generate the SI API. So this happens every time I do a commit to this directory. So I'm kind of showing the top level takeaway. We can get into some details. See this badge here? So it's called a badge.
Mm-hmm.
This is automatically rendered every time the pipeline runs, so you can see at a glance the status. If you are familiar with Sonic build image repo, there's a whole slew of these for different things being built. It gives you an at a glance status. So the idea is if I do a commit and a push to my fork, I'll get this behavior. Likewise, if I were to do a pull request on a build, on a repo, for example, when I submit this pull request, if someone looks at the pull request, you should see that this did pass or did not pass before you even decide to accept it. And we haven't gone through that workflow yet because this is the first pull request with this capability in. So once this is accepted, once we accept this pull request here, this automation will then be in the main Azure Sonic Dash branch, and then it will do all these things for us. And we'll go through that after we do a merge of this, whenever that happens after the review, and we'll watch how it works. So any questions up to this point? We're covering a bunch of new concepts here. Okay. So what I'll do is I'm going to go to this actions, and I'm going to go into this branch here, and I'm going to.
So I do have one question for you, Chris. If
Right.
you were a longtime Sonic developer, how familiar would all this look to you?
I think pretty familiar. I mean,
Okay.
someone's welcome to disagree, but none of this is exotic. It's really just familiar, conventional concepts, and Sonic's using some variant of this.
Okay,
already.
good.
Yeah. The main difference is Sonic is using some build resources like Git runners that are allocated and much more high performance than the freebie ones we're using right now. But yeah, this is nothing here is departing from convention as far as I know. So I'm going to go in and edit in place this P4 file. And I'm going to, this isn't normally how I edit my code in GitHub. I usually do it in an editor.
But we're doing it on the web.
Yeah, because this is a private branch. I mean, this is a fork, and I can do whatever I want. So if I do that, and then scroll down, commit changes. And I just committed it, right?
Mm-hmm.
And let's see what happens. Look at that. It popped up in the pipeline in real time. I didn't have to even refresh the page. See that? So this is running right now in progress.
Mm-hmm.
Now, one thing about this, it takes about 2.5 minutes to pull this Docker image. I'll talk about that while this is running. Once it pulls the Docker image into the GitHub runner and it's pulling it from the cloud, then the first thing we'll do is build the P4 switch. So while we're waiting, let's just look at a couple of things. I want to show you what's going on in terms of the workflow. Okay, so here's the Sirius pipeline top level README where I've tried to add a lot of documentation to explain everything, what's happening. And I do hope that people get a chance to review this and be critical and find things that aren't clear, spelling errors, whatever, ask for more information and file an issue. Because my goal is to make this so that it's standalone and you don't need me anymore. Doesn't mean I don't want to work on this. It's just that's to me the real litmus test is this complete and you can do it without any help. That's what I mean. Mm-hmm. So there's all this documentation, and what I want to do is just jump to this diagram that shows the workflow. And I'll just expand this a bit. So in this Docker build, we pulled from a registry, which is Docker Hub for now, but hopefully it'll be it'll be Azure Container Registry or ACR in the future. We're pulling this into our work environment on demand in the GitHub runner. If you run it on your local machine, it'll do the same thing. So this GitHub runner is doing basically what you can do on your own if you clone this repo. You can do all these same steps. The idea is automation and step-by-step manual development should be virtually the same. So you don't have to wait to do a pull, to do a commit and a push to try this pipeline. You can do it on your own machine. It just won't look like this. You'll see it on your terminal, all the steps. So we're pulling this Docker in, and this Docker is basically a slightly modified version of the one that Marian's original repo contained, whereas he was building it on demand in the user space. I built one and uploaded it to Docker Hub so that you can just pull it on demand, because this takes an hour or two to build. And it's much nicer just to download it in a couple minutes and have it on demand all the time. So this is the environment, and this is the builder. I'll explain that in a minute. Okay, see that? It took 2 minutes and 40 seconds to pull the image, 1 second to compile it and say, I don't think so, right?
Mm-hmm.
So we did that. And what I'll do is I'll exit from here for a second.
Hey, Chris, just a quick question.
Yes.
How do we keep the Docker image up to date? In other words, you know, between the forks and between branches, you know, the dependency might change, and then you may need a different version of the Docker and so forth. Do we have any type of means to ensure that, okay, we have the right version put in anytime we want?
Yes, I'll commit this. That's a good question. Let me make a note real quick so I can remember to configuration management of Docker images. That's how I'll summarize the question.
Sure. Yeah.
So, question. Let me go back to this README to put this in the context. So, how do we know that this image that we pull right here is the right one for our build environment? Well, every Docker image has a tag. So the name of this Docker image today, the full name is the name of the repo / and that repo right now is named Chris Summers, because that's my personal Docker Hub and that's where I'm storing it, / and then the name of the image -bmv2. And what I'm not showing here is the default : tag, and the tag is latest. So right now this pulls latest, but that tag can be anything we want. It can be, you know, version 1.24 or whatever. So what we would do is when we actually get into using this workflow, hopefully we'll have a different place to store these images. I can host them for now, but we'll version them. And so a particular snapshot of this entire project, of the Sirius Pipeline project, itself has a version, right? It's the version, it's the SHA commit hash of the Git repo, or we can give it a branch. That will have an explicit tag for this as well. So they're all pinned together. So everything can be pinned to one reproducible snapshot. Does that make sense? Or do I need to try again?
I think that's a good explanation. Thank you.
Okay. So let's see. We're rebuilding. Yeah. You had a question?
Repo level, or even at the, yeah. So just a quick question. Can you hear me, Chris?
Yeah. Yes, we can.
Okay. Sorry. So as you were describing, if something gets committed in committed into a branch, so to speak, And in your case, for example, that you just mentioned, like the P4 file, do we have some level, some dependency, which ensures that, you know, if you are modifying, let's say, a non-code file, for let's say a documentation file, then you don't need to go through this entire, pulling of all these other artifacts and building this entire thing and so forth, right? So how do you go through this kind of a dependency checks to say what exactly the actions that you need to do?
So for example, if I modify a README file, I don't want to rebuild this, right? Is that the
Right.
kind of, yeah. So yes, the answer to that is, it's all very, very much controlled by files under GitHub workflows. So here are two CI configuration files. So this one is for the pipeline we just ran, and you see it passed, right? I fixed the do.p4. This is for the main series pipeline. This is actually for the Docker file itself. So if I make a change to the Docker file, it will actually build the Docker file to make sure it builds. And when we get the proper final resting place for this Docker image, we can actually publish it automatically to the Docker repo. So if you change the Docker file, it'll do a build of Docker only. If you change any important code in the pipeline, and it will look at that. And this is something that's subject to everyone learning to do if they wish, and make improvements along the way. But here's an example. It's pretty readable. It's YAML. So on a push, any branch, these paths change, that accept the Docker file and accept README or MD files, then run the pipeline. Likewise, on a pull request, the same thing, and on branch main. So we can change these things as much as we want to fine tune it to our, let's say, day-to-day workflows. And then here's the jobs, the actual steps that are happening. So it's just a description. It tells it to run it in an Ubuntu 2004 instance. It's got some environment variables, working directory. Okay, so here's a bunch of step-by-step things. Now, as a user, I might just type make clean all to run everything all in one command, and I'll demonstrate that in a bit. What I did here is we broke it down, and Deanna did this work. Broke it down into individual steps so that if something fails, we broke it down into all the steps, because it's much more easy to debug things if it's broken down that way. I could have just had one job that said make all, but then you'd have one thing running and running and running, and you wouldn't know how far you've gotten unless you read all the detailed logs. So here you can see all the steps. So see this install site submodule. So that corresponds to this step. So a job consists of steps. So here we install the site submodule, and the actual command is this command, just like you'd type it on a command line. So these are all basically shell commands. Pull the Docker image, so I pull it. Run the software switch, build the software switch, so does this make P4 command with some flags. So these are all the steps, and this is something that once you see a working version, it's not hard to modify and make changes to. It's easy to learn. I'll pause for questions. Okay. So I've demonstrated, two basic things: committing a bad and a good build, and that's kind of the big takeaway for this. But I want to mention something else now. I'm going to get to the next level, and I'm doing this kind of at let's say a superficial 20,000 foot level right now, so we can cover the highlights, because we could drill down into any one of these things and spend a whole meeting on it. And so I want to make sure we cover the main points, and then we can dive down more, or you can read the README and hopefully come up with questions and learn along the way. So I want to show something here. Get to this one. See, in this job, we built all this stuff. We built this C++ test, and it's the same test that Marian created originally. All it does is, well, I shouldn't say all, it does a lot of cool things. It compiles the P4. It auto-generates the Psi API to the series pipeline. It's really clever. I want to pat Marian on the back for that. It uses Jinja 2 templates, generates all this headers and bindings to P4 runtime. So it creates libpsi, which is the fundamental, interface between Dash data plane and Sonic. Builds a simple test which just does basically one table access. It doesn't send any traffic, but it proves that the whole stack works. And when I say the whole stack, what I mean is it builds everything here up to libpsi. So it's building. This here is pulled from the p4.lang. That's actually the base of the Docker image, is this behavioral model. This is the vanilla behavioral model v2. It's not the modified one that the behavioral model working group is working on. This is vanilla BMV2, and I'll defer to Marian when we start talking about how to migrate to the modified one. It comes with P4 runtime server. So this is the native data plane interface to behavioral model v2. So Marian created all this, which is auto-generated from the P4 code. And in a little more detail, it's actually generated from the P4 runtime metadata that the P4 compiler creates. So P4 code is compiled, it creates P4 info, which describes all the P4 objects or entities, tables, registers, counters. That gets generated into all this code. What you need is something to interface to this libpsi, and normally it'll be syncd daemon in Sonic. But for this testing, we intend to use a Psi-thrift server, which allows you to make remote procedure calls to the device under test. So the vendor would compile their libpsi along with their entire data plane implementation, which is not going to look like this. It's going to be something else. It's going to be your system on a chip and all the libraries and your own code. And then we'll have a Psi-thrift server to be able to talk to it with test scripts. So back to where we are today, there's a simple C++ program called vnet out that replaces this for now, and it's linked to libpsi, and it makes one table access through the stack. That is what this test Psi library step is. So if you were to drill down and look, it just runs this make command, make run test, and it does one simple gRPC access over P4 runtime through a libpsi. And you can look at the code for this. It's pretty straightforward. It's just setting up a Psi table entry and writing it. So that's the first test. And that's been in place for some time. This is all new. And what this is we're spinning up some software traffic generators in this place. And we're sending UDP packets in and expecting them to echo back out. I remember that was Bud's suggestion. That's our first hello world. And without configuring this, it should just echo UDP packets back by default. And I didn't mean to do that. What I want to do is show you some scrolling. So these are all the instructions. This is the configuration of the traffic generator. And I'll explain this a little bit, but to learn more about XCSC, you can follow the readmes and the links. There's an open source repository on GitHub called Open Traffic Generator, and this is described there. You can pull it. It's a Docker images, the free version. You can just pull them down from Docker Hub. And this is the layout. There's several containers that comprise the controller. This is one Docker image, and then there's a Docker image for a traffic engine, and you spin up instances of all these and bind them together. And this is flexible. You can have many traffic engines. You then bind these traffic engines to V Ethernet ports. And these are spun up. We create these virtual Ethernets and bind them to BMV2, and then they're linked together like this, so we can send traffic in and out. And yeah, so this is kind of the setup. In this controller, this is actually the Open Traffic Generator API that I've mentioned in the past. It's actually specified by an open API Swagger-like document, and this is actually an HTTP connection. It's a web UI type interface, but I wouldn't say web UI. It's a typical, HTTP interface. This client is a Python library or a Go library. In this case, we're using Python. So it's snappy Python binding. And this is a very easy to use library. So what you do is you import this library into your test code and then talk to this traffic generator complex. And it doesn't take very much to learn how to use this. So this is the layout for the traffic test we're about to do live, and that's in here. So we created one test case. I can, Alex, did you want to say anything about this at this point? Alex Bortock's my colleague, and he's been helping with this as well. I didn't mean to catch you off guard, Alex.
Yeah, you got me a little bit off guard. Yeah, well, definitely. These are like the low-level details of how the XCSC traffic generator, like what are the components it consists of. Really, to use it, there is a good way to hide all that complexity and just have the API that your test script talks to, and
right
then
you
have the and then on the right-hand side you have outputs that are sending packets to the behavioral model and back. The interesting angle to that is the same API that we use here with the free version. You can use it with the hardware traffic generators. So
yeah.
that when you want to move that into the actual physical test, and your test content doesn't have to change.
Thank you for pointing that out. So this can be replaced by a hardware box that runs at line rate, any speed available, up to 800 gig at this point. So then the same program will work. So that's really why we're making this investment in doing this. It's not that we're trying to push this as much as we want a workflow that goes from software in the cloud testing to full line rate on the test bench or in the production with the same code.
That's awesome. Awesome. Really like that.
And you follow the links. There's a whole repo on this XCSC and Snappy, and there's example programs you can get up and running. So in fact, I wanted to also extend. So Alex has been helping me with this, and Deanna did all the automation work. I've been doing kind of the polishing and the usability and the documentation. I also had a lot of help from Madhu. I wanted to give a shout out to him. He just joined this last week, this Dash project, but he did a very thorough test drive of this repo the other day and gave me a full report and caused me to make a lot of little fixes, because when you do it in your own workspace, everything always works. As soon as you give it to some unsuspecting user, you find all the things you assumed. So we run this test, and then that's complete. So when you push a P4 code change, it's also going to run traffic through the pipeline every time the pipeline runs. It's going to do some tests, and we have a very trivial test right now that's not really testing Dash. It's just testing kind of UDP, echo, and connectivity. So now it's up to us collectively to start creating meaningful tests. But now we've got the infrastructure to do it. And what I want to do next is I will cross my fingers and try to do a live run of this, because I did it just 5 minutes before the meeting and it didn't pass because my VM is so slow, the test timed out in 10 minutes. So bear with me as I try to do this live. But we know it works in the cloud, and these test runners, the free ones, it's just 2 cores. You only get 2 cores allocated and 14 gig of memory, which we're almost using up just for the Docker image. And so it's pretty underpowered, but it manages to run. If it doesn't run on my machine, it's because my machine's even wimpier because I'm just doing a VM in VirtualBox. So this is one console. I'm in the Sirius pipeline. Hopefully this is big enough to read. I can, is it too tiny? I can make it a little bigger.
I can read it.
I can
I'm
read it
old,
if I
so
squint,
you're
and
good.
I'm old.
Let's get rid of the squinting. Let's see if I can. Did that help? No, it didn't help. Come on. Don't do this to me. No, close. Should have. Oh, there, bigger. Okay. So I'm in here, and let's say I just cloned this repo. I would do make. When in doubt, make clean. I'll make clean first. Okay. It doesn't do that much. It just deletes the things like some B Ethernets, deletes the built C++, cleans up some things. And it also restores the SCI repo if it needs to. And I'm going to make all. So first thing it's going to do is run the P4C compiler on the dash P4 code, the Sirius pipeline. And then it's generating the SCI API.
Wow.
Yeah, it's that fast. I mean, the P4 code gets compiled in a second. This runs slow on my machine right now. This is much faster on decent machine. Okay, and then it ran and then built the test program. That's it. We just built everything.
Wow.
Pretty easy, right? I'm going to make network. And what this does is it creates V Ethernet pairs in order to connect BMV2 to the traffic generator. So it just does a bunch of IP link commands. People who are used to virtual Ethernets won't be surprised. And it's disabling IPv6 on these because when you're doing behavioral modeling, if you don't do that, you start getting neighbor discovery calls to your V Ethernets automatically by Linux. Thank you very much. And it's kind of annoying.
Yeah,
So
you don't want. Yeah.
I'm going to run switch. So this will spin up Docker image. And by the way, all these steps, all these build steps are being run inside Docker, one step at a time. All these make steps are run in the Docker image. So all the tools are in there. They're pre-built. gRPC, P4C, all these huge tools are all pre-built, and you just download the Docker image. It saves hours of building, and it's reproducible because it's a frozen image. So we're going to run switch. Okay. So we've got a P4 runtime server in the switch waiting for P4 runtime commands. And that corresponds to that diagram of that stack. Now in a different console, because this is running like a daemon and it's spewing stuff out verbosely, I need another console. I'm going to type make run test. And this is the C++ trivial libsci program. All it did was do one table access. Let me show that code so people know what I'm talking about. Okay, this is Marian's test code. There's just a bunch of definitions, but really it's just a simple program main. It creates a couple of SCI entries or one. So it does some kind of a table access and
Direction lookup. Yeah.
and sends it, does a couple of things, and then sends it to the data plane. Okay, it basically just makes sure that it can talk to the libsci interface, but it doesn't try to send traffic. So we just ran that. Right here. Now I'm going to do the scary one where I'm going to cross my fingers so I'm not embarrassed.
Mhm.
And what this is going to do, now I've already downloaded, because I ran this several times, I've already pulled the Docker images for XCSC, but the first time you run this, it'll install dependencies, and that includes the Snappy Python library. and it pulls two Docker images, one for the XCSC controller and one for the traffic engine. So it does those dependencies. Then it's going to spin them up in that configuration I showed you, and it uses Docker Compose to do that, which is a nice declarative way of, instantiating containers. It's a YAML file. So you need Docker Compose in your work environment, and I explain all that in the README. So let's run the test and see what happens. Okay. It's sending traffic, and it's sending 1,000 packets. Here's the BMB2 pipeline output. It's still spewing to the console because it's so slow to emit it. And what it is, it's sending 1,000 packets to each port and making sure that 1,000 packets come out. And it's looping. It's saying, okay, how many packets have I sent? Does it equal the number? Did I get at least as many out? Right. And it's getting more out because there's other stuff going on, and I can't get into that right now, nor do I fully understand it, but there's more packets than we transmit coming out. And that actually might have to do with the environment. But we actually spin up and send 1,000 packets, and we try to send them at a higher rate than the BMB2 can actually handle. That's why it takes a while. If this were running on a faster machine, this test would run much quicker. But basically, we went through that whole process, with the make run XCSC test. So ideally, we'll have a lot of tests in the future that will continue to run more and more tests, and I'll show you where these tests live. So
Why
under
did
the main,
we have separate rows? I'm sorry, I missed that.
yeah, I didn't explain it very well either. What happens is we tell it send 1,000 packets, then we start looping and waiting until all the packets go through.
Oh, okay.
So
Okay.
it's just saying, okay, in this
So
example,
iteration 1, iteration
Yeah.
2.
it
Okay,
just keeps
thanks.
looping every few seconds or every
Got it.
polling. It's just polling. So it's just waiting to completion. It doesn't know how long it's going to take. So it's just waiting until it gets all 1,000 packets sent.
Cool that it
So-
works.
Yeah. And so let's say when we start testing for real, the dash data plane, like VNet service, we'll craft specific packets and send them, and then when we get them back, because this has a capture engine, we can actually dissect the packets and make sure the contents are exactly what we expect. This is a real trivial test, just a hello world. So it proves that everything's wired up and functional. So the next step should be to start talking about real tests. And where this lives is under the test directory. We have test cases. And this is the test hello world icon. And you can look through here. It's just an example of setting up Snappy, and there's various primitives in here. It doesn't look like Scapy at all. If people are used to PTF and Scapy, this won't look familiar, but it shouldn't look too foreign either. It's just a matter of learning the conventions. But there's a number of things in here I want to point out that you won't see like in PTF and Scapy. Here you can say how many packets to send. You can actually set the data rate. Now in this super slow VM that I'm running, you're not going to be able to get 1,000 packets per second, okay? What you'll get is whatever you get. And we're running it right now in a mode where the transmit engines are sharing, both transmit engines are sharing a core with the controller and the entire test program and BMB2. The receiver is pinned to one core because the receiver needs a full CPU to run. You can see us constructing a packet, setting the values. Now here's something that's really cool. You can set up pattern generators in the different fields of the packet. So for example, you can say, I want the port to start at 5,000, increment by 2, and do it 10 times, and then loop around. So you can actually create sequences in just a few lines like this. That's really the power of this data model. And you can create destination port lists. So there's all kinds of little syntactic things in here that are nifty. And once you get the hang of it, you'll find out. And then here we're getting the metrics from the receive engine, which is all kinds of counters and statistics measured automatically. And then you can pull those. And for example, in our test, we're saying, get all the sum of the transmit packets, get the sum of all the receive packets, and make sure that to finish, we're done when we've transmitted all the total transmit and receive packets meet this criteria. But this is just an arbitrary function. You can do anything you want. So there's all kinds of nifty things in here. And if you want to learn more about using this, there's actually a Slack channel for XCSC support that we host. So you can get help. Plus, there's demos and examples online. So yeah, so I ran the demo. I walked through some of this. Again, this was the engine. So let me pause and ask if there's any questions at this point. I could walk through a little bit more of the pull request if you like, or we can, end here, and then you can clone this, look at the pull request, and learn more, because there's a lot to take in here.
So I guess one thing that looks like it would be easy, if we wanted to write a test for the TCP state machine, it looks fairly straightforward. We should be able to generate packets and make the TCP state machine go through every single state and then ask for the state back as we transition to see if the state machine matches our behavioral model. That sounds like it would be relatively straightforward to go and test the machine.
Well, I guess what I would do is defer to whoever wants to talk about the behavioral model and see if you can query its state at any point in time. But what we can do is create arbitrary sequence of packets, right, with their exact content, send it,
Right.
One at a time or in a batch or whatever, and then decide what comes out. But essentially, what we're doing is sending packets in and out like a black box. So as far as reading what the state is of the state machine in here, I'm not sure that we actually have an interface to be able to do that. It's indirect, but someone else wants to comment on that. Would there be a P4 register or state variable? Do we need to define an interface that lets us read the state one at a time? I don't know the answer to that question. I know the indirect.
I think so, but I don't know. I don't know if the people on the call
Marian's on the phone. Marian, do you know of a way to do that? Or should we ask the P4 community?
I think
in general, we have to be able to read not just TCP state, anything, counters, you name it, out of the implementation. So there has to be the API is needed to do all of that, and we need to be able to test it. So I don't see this being any different, as long as the TCP state is supported, of course. So there'd have to be an API for it.
Usually you would do that with for runtime API, but since we have this layer on top, which is the -sci API, maybe we should support it there.
Yeah, right. And if you want to read some internal state, if it's not part of the SCI, specification, then you can't really read it. This is all just kind of an implementation that's buried. This could be a system on a chip on a DPU card, right? So I don't know if we've identified internal state variables as being exposed here. A lot of times they're buried in the implementation. You may not even be able to read them necessarily easily. In order to expose them with this structure we've created, by definition, either we'd have to have a handwritten SCI interface for those state variables, or we expose them in the form of P4 pseudo tables, let's say. or registers. You know, we could have named registers that give state. But
Or we could.
Hopefully
Sorry.
we can just get it through the SCI interface. I'm not understanding why we couldn't. I don't think think that they have to support the TCP state machine, and that's why it's being donated and worked upon, and we need to be able to read its state for sure. Otherwise, I don't know if they've implemented the state machine properly.
Marian, I don't know if you're
Mario
trying to,
was-
but it sounds like Marian's trying to say something, but I didn't hear it.
Hi, can you hear me now?
Yes.
Yes.
My question is, what is a state per connection for one?
Your voice is cutting in and out. We really can't make you out.
He said something
Yeah, it
about
would be
state
for
per
it would-
connection.
Yeah, Mary, it would be per connection, and it would be to validate the function of this. So it doesn't have to run very fast for you to be able to generate packets to create all the different states of the TCP state machine. You should be able to create the packet and then read the state, and I should be able to create packets that make no sense and see what happens to the state machine. Like, I would want to ensure that that state machine is robust, and so we should have an API, and we should have the ability to always be able to read the connection state. Now, whether in live traffic, that would be kind of hard because connections might only live for a fraction of a second. But for functional testing, of course, we should be able to read it, because we can generate those packets slow enough, and basically one packet can cause an entire state change, and should in fact in many cases. And then that way we can look at this. You know, it's an easy test to do because we have the state machine and we have all the transitions. We can generate the packets. Now we need to make sure that the implementation is actually creating those states and transitioning properly. So I think it's super valuable to make sure that we're not, basically Keysight mentioned a whole bunch of different scenarios where states were transitioned and after so many seconds and all that kind of stuff. And it's something you really do want to test.
Yeah, Gerald, I
So
totally agree. I just don't know that it was ever like stated as a goal of the behavioral model. So we'll probably have to bring that up in the behavioral model meeting, that's saying these are objectives, right? And may have to take another look at data plane.
Yeah.
I couldn't agree more as a test guy, right? It just
I don't think that this is an issue, I mean, a matter related to the behavioral model. It's more a matter related to the API itself, to the Dash API itself. If we want to expose this, we have to add it to the Dash API.
Yeah, I guess behavioral model, we're overloading the term. We're not talking about the implementation as much as the definition of the API.
Yeah.
Behavioral model, external interface, whatever it is. And so, yeah, let's dig into that when we can at the behavioral model meeting.
Hi, Marian.
Hey.
Are you trying to talk
yeah,
again?
so that's yeah, can you hear me now?
Yeah, go ahead.
Oh, good. So that's a bit of an issue, because when we are talking about the API now, it will be a new requirement for vendors actually to expose the state of every connection to the control plane. And this is not very useful at the high rate. So doing that at a low rate only for the testing, it seems to me as a requirement that's not going to be actually APIs that are not going to be actually used in production. That's my point.
Yeah, but they're they're used to get into our production. I don't want something going into our production that I can't know that there's even a proper TCP state machine. And that's, you know, so it's not a matter of production. Production, you're not going to use that API to figure out a state of something that lasted a fraction of a second. But to get into production, we need to know this stuff works.
Yeah, but we can define tests that way.
Black box
with
test.
the Yeah. Without looking at a connection, we can look at the actual behavior that we know for certain that after a given event, a connection should be removed because this is the end goal of the state machine, or shouldn't be removed. And then verify if it is removed or not based on sending another packet that belongs to that flow data packet.
So Marian, are you talking something like a Codenomicon or something like that that does a TCP state machine check to ensure that all the transitions are kind of kosher? I mean, are you looking at something, or
I mean, that's what
is that
I'm wanting.
right? That's not going to happen from the API side the way we are setting up here, right, Gerald? I think that's a little bit more white box, protocol correctness type of a test to ensure that all the transitions are kosher across, various edge case scenarios, right?
Yeah.
So how is that different from querying the state from the state machine?
Sorry, we can hardly hear you, Marian. You cut in and out.
This is maybe a good topic to pick up on next time then. We have 6 minutes left in today.
We can bring it up in the behavioral model.
Okay. Okay.
Because once we start writing real tests, we have
Yeah.
to, there'll be categories of tests that we need to write.
Yeah.
One of
So
them,
Chris,
needs to be this behavior, but there'll be many other things that will, we can break out those tests and assign them to different people to write, but okay, but it's a good topic and we can bring
yeah,
it up in
it's
the
a great
behavioral
topic.
model.
And Chris, maybe you can attend the behavioral model meeting and remind me. Yeah.
Yeah,
Okay.
definitely.
Great.
So I just wanted
Great.
a couple minutes to
Yeah.
wrap up, if that's okay.
Yeah,
Gerald?
please do.
Good point, Gerald, because it may force us to rethink the behavioral model API. So just, I'd ask people to take a look at this PR and try it out. What you want to do is go to the, pull request itself where it specifies it, and oops, let me go here. You want to go to the pull requests, and then when you see this one here, this is the pull request. You can go to this repo and clone that. Then that's going to be that's where you can actually download and try this before it's committed to Dash. And Bud, to answer your question, the data plane configuration is actually the test that runs before that, the VNet out. So the test that Marian wrote on the lib side, that has to be run first. We found empirically. We can follow that.
Okay, great, thanks.
Yeah. And so next steps, we need some more tests written. We still need a SciThrift server, which I want to start working on, resuming on that now that we finished this pull request, which was quite a bit of work. I want to start working on the SciThrift server again, and I'll need help from people who are experts in that because it's not my wheelhouse. And I think someone's doing something very noisy in the kitchen.
Oh yeah, 40646. I'll just put him on mute.
Okay. So SciThrift, we need a proper Docker repository at some point. There's actually a whole bunch of to-dos here that I've put in the PR itself. There's a couple of known issues, and this, Bud, relates to your question. We have to run this first test before packets will echo back, and it may be obvious, people who know the model better than I do. This Docker image is too big. We need to trim it down, and there's well-known techniques for doing that. If anyone wants to take a stab at that, I've put some ideas on how we can do that. Otherwise, I may work on it in my spare time, but it's so big that it's going to exceed the Azure free runners. We start adding
Hey, Chris,
code.
maybe if someone wants to work on it, they could ping you and let you know so
Yeah.
that you both are working on it at the same time.
Definitely, I'd be happy to have a one-on-one dialogue. So here's just a whole list of like going forward next things to do, right? Chris needs to learn how to spell. That's another to-do. So anyway, there's a bunch of things here. People can take a look. And, you know, hopefully we can use this as the basis going forward. I have no objection to people writing traditional PTF tests because they're convenient. You know, we can have multiple types of tests in this repo. So if that gets you up and running faster, go ahead, and then we can translate them possibly into the XAC snappy version by using, you know, whatever you did in the test so that we can eventually scale it to line rate. I didn't have much time to talk about the Git submodules, but there's a lot of implications. Previously in the Docker image, Marian would pull the Git, he'd clone the Psi repo into the Docker image while it's building every time on demand or as needed. And instead, I'm doing a Git submodule, and I talk about what that means in the README. So people, if they don't know what that is, they can learn a little bit about it. Talk about submodules down here at the bottom. Here we go. But they're used extensively in Sonic. I mean, the Sonic build image is nothing but Git submodules and some make files. So you can learn about that if you like, but it's a way of pinning a version of Psi to this project so that they're always in lockstep. So we tried to build in configuration management and make sure that we can always have a reproducible state of this repo. So if people do changes along the way, no matter what happens, you pull out a certain version of this repo, it should all be intact and all the versions should be tightly coupled. So that's all I have to say about this today.
Thank you, Chris. There's a question for you in the chat that maybe you can address at some point. I'm going to stop the recording. I do have a hard stop.